Good morning, everyone. Welcome to the CTS Transportation Safety and Traffic Flow Research Council meeting. I'm Steve Miskin, I'm the council chair. Also MnDOT's Metro Traffic Engineer. I'd like to introduce my co-chair, Tony.
Hello, my name is Tony Fisher. I'm a highway planner at the Met Council and I'm vice chair of the CTS Transportation Safety and Traffic Flow Research Council.
Thanks, Tony. Today we have two speakers, and I'd like to point out that these this CTS Transportation Safety and Traffic Flow Research Council provides a forum for transportation professionals and researchers to exchange information on current issues and trends. They bring together university faculty and staff with practitioners from the public and private sectors to recommend direction and participate in improving the center's research, education, and engagement programs. With that, I'll toss it over to Katie.
I think it's over to me, right? Good morning,
Okay.
Everybody. This is Gina Boss. I'm the Associate Director for Engagement and Education at the Center for Transportation Studies, and want to welcome everybody to this seminar and meeting of the Safety and Traffic Flow Council. So a couple of housekeeping items that we wanted to run through. So one is, if you have questions for the speakers, you can use the Q&A feature to submit questions and comments, and we will go ahead and answer those during the Q&A time. If you'd also like to use chat, you can put your questions in chat as well. When we do get to the round robin, we actually have the ability to kind of call on you. So we will ask you to type into chat, I'd like to share, and then we'll unmute you and you can verbally share your questions. For any students who are joining today, we'd like you to send in the chat message to all panelists that you are a student, because we do keep track of how many students attend CTS events. And then finally, today's seminar and council meeting does qualify for professional development hours for engineers. So if you need some kind of certification for that, send a chat to all panelists with your name and email, and we'll email the form to you. If you are also interested in AICP, continuing maintenance credits, do the same. Send a message to all panelists with your name and indicate that you're interested in AICP credits. All right, and with that, I'm going to turn it back to Steve. Or am I doing one? Yeah, nope. To talk about the rest of the slides.
Yep. First of all, we are recording this event today. We will be posting the video recording on this event page later, along with the slides of the presenters. And I'd like to also remind people about the research conference that's coming up November 5th, a little over a week away. Deadline for registration is Friday. It's very reasonable registration fee of $40. You can see the link on the screen, click on that and register. Looks like a great program, many great speakers. We also have some upcoming webinars similar to this one next week, how transportation can reduce Minnesota's carbon footprint. Again, you sign up by clicking the link. With that, I will turn it over to Tony.
Okay, I'm going to introduce the presentations and the speakers today. So the presentation will feature a brief overview of a project funded by the National Science Foundation on a smart cloud commuting service via shared autonomous vehicles. It will highlight two preliminary studies exploring the feasibility of the envisaged smart cloud commuting service. The first study includes the development of a queuing theoretical model to determine how many shared autonomous vehicles are needed to serve peak commute demands. And the second study involves a proposed hybrid spoke and hub with point-to-point transit service model that leverages the flexibility and autonomy of shared autonomous vehicles. Jili Zhang is the Associate Director for Research at the Digital Technology Center and a distinguished McKnight University Professor and Quest Chair Professor in the Department of Computer Science and Engineering at the University of Minnesota. His research interests include computer communication and networks, internet technology, multimedia, and emerging applications. Yanhua Li is an assistant professor in the Computer Science Department and Data Science Program at Worcester Polytechnic Institute in Worcester, Massachusetts. His research interests include artificial intelligence and big data analytics in many contexts, including urban intelligence, smart cities, and urban planning and optimization. He is a recipient of an NSF Career Award and an NSF CRE Award. With that, I'll invite Zili and Yanhua to present.
Tony, thank you very much. So let me actually share my screen first. Can you actually see my screen?
Yep.
Looks good. Thank you.
Okay.
I think
So-
right now we can see the presenter view.
Okay. Mhm.
Yeah.
Let me just restart. Okay, that better?
Great.
So again, first of all, I'd like to thank the CTS and Tony for inviting us to give basically an overview of our project. So, so I'm gonna spend, let me actually just show you the outline. So I'm gonna spend probably 10 to 15 minutes, give you an overview of the project, the motivation and the vision of the project and what we actually propose to do. And we're going to then spend probably 20, 25 minutes to talk about some of the research activities. We're actually gonna talk a little bit more than what Tony just talked about on the feasibility study and the hub and stop model. Since this is actually involve a large team, so we want to actually cover, briefly cover a number of other activity going on done by my colleagues also. And the part of the purpose of the projects, not so much just to talk about what we have done, but we actually also like to getting some feedback, comments, and also getting collaboration possibly. So we're going to look at also some of the challenges we're facing. For example, how do we actually evaluate the impact and the outcome of the research, right? So in particular, in terms of data, how we can get the data to help our research. In particular, since we're actually looking at the future AVs, which is not there yet, a lot of things we are doing are basically based on projection, our imagination, what's going to happen in the future. So we're going to conclude the kind of the talk by just briefly talk about some of the projects we are looking at, the newer one, looking at a more data-driven AI-guided approach, look at transportation service. So my former student, Yan Hua, can actually talk more on one of the projects. Then we're looking at not another one. We are just started looking at how to apply AI to do modeling demand, etc. So the talk going to be split between me and Yan Hua. So let me just kind of say a few words about our National Science Foundation project. So this project was founded about 2 years ago, essentially $1.75 million over 3 years in the context of the NSF Smart Connected Community Project. So the projects actually involve a relatively large team of faculty from University of Minnesota. It's an interdisciplinary research project on the computer science and the College of Engineering and the science side. Besides myself, we have Saif and Alireza and Yan Hua, who's a former student graduate from UMN, now he's WPI, he's the data science expert. We also have Yingling Fan and Frank Duma from Humphrey looking at the social policy issues, and also Tom Fisher looking at the urban design and other infrastructure related problems. So the project itself involved both kind of two important tracks. One is looking at a research problem. Other part is it's like involve community engagement, talk to the community, understand the problem, etc. So I just want to kind of say a few words of the project partner. We actually recruited a large number of community partners, in particular, Minnesota Department, the MnDOT, and several organizations within MnDOT, such as Met Council and Metro Transit. We also have Southwest Transit and a number of other organizations. For the interest in time, I'm not going to kind of list all of them. I mean, name all of them. So the motivation for our project is basically the premises. We basically recognize the driverless car are coming. For example, most of you probably have heard in the news that Google, Waymo, and Uber actually has already having some trial using AV to actually ferry passengers. So whether we like it or not, we believe AV is going to have a huge impact on the society at many levels. So for example, how we actually going to own a car. Once you have AV, you actually buy your AV, just have it sit in your parking lot or in your driveway most of the time. And AV also going to change the way how we actually design future transportation system, mobility service. We also going to have a lot of impact on how we design the physical infrastructure, the highway, urban streets, even the parking and the land reuse issue. Right? So we probably don't need a lot of parking spaces since AV can actually go somewhere else instead of park on the street. So other kind of aspect we're actually interested in looking at is the impact of AV on a lot of social issues. Right? So it's going to impact the business, how people actually going to live and come to work, but also the technology have and have not. Right? So the social equity issues. So in particular, we believe that just like internet has transformed how we access information and actually interact with each other in cyberspace, and also early days of internet had created the technology divide. Right? So people have internet access versus people don't have internet access. In particular, this is actually the social equity issue showed up in this pandemic, COVID-19. A lot of low income kids actually don't have internet access, so the online teaching they can have problems. Right? So the similar issue when you have AVs, would we have a situation only a few people who can afford and have AV, where majority of people do not have AV? Right? So that's the kind of bigger social problem that drive the project we are actually interested in looking at. So that's why we actually, even though AV is not a commonplace yet, we want to look at what are the kind of issues we need to address about, and how can we actually leverage AV to address some of the problems. So the project actually not so much about how to actually design AVs. Right? So we actually take the AV availability of AV as given. So we're looking at how can we actually leverage AV to design a kind of transformative transportation mobility service based on the idea this AV is going to be actually shared, and most people probably not going to own AV necessarily. For the future smart cities, so we can actually bridge the technology and the geographical divide and try to bring the benefits to the diverse communities. So for that purpose, we're actually working with a stakeholder, policymaker, community, try to identify and tackle various social economic challenges and kind of imagine how we can leverage AV to solve that problem. So kind of, we believe actually the state of Minnesota, Twin City area have a kind of reputation for forward-looking reputation to address some sort of problem we have to look at. So this is one of the reasons, in fact, actually National Science Foundation awarded the 2 large NSF for smart community project to University of Minnesota in 2 years in a row. At the time we actually got the award. In fact, actually We actually have 3 projects that are awarded. We have a new one, actually working with faculty who was at the University of Minnesota, but recently moved to CMU to have another project related to this problem. So anyway, so I want to kind of talk about our vision for this project. So the idea is basically we want to leverage a giant pool of shared AV to provide new kind of mobility service to bring benefit to the citizens. Right? So this is going to be aided by the advances in mobile cloud computing, big data, AI, etc. So we believe that's actually possible. So part of the kind of project we are looking at is not, for example, designing yet another Uber or Google Waymo type of service. We actually want to target the peak demand, so I try to address the daily commute. So most people actually own a car because we need that for daily commute, go to school, go to work. That's also the reason you create congestion and also pollution, etc. So the idea is how can we actually thinking about essentially leverage economy scale and design system people can actually use for daily commute purpose, which is also give us a lot of kind of economic system efficiency, we can drive down the cost. So obviously, how do you do this things is going to be the challenge that we actually want to look at in this particular proposal. So the overall goal is basically say, the question we are asking is, can we actually design such a smart cloud commuting service in such a way that it can service a diverse community, not just a particular neighborhood, a particular community for people can afford it, to enhance the economic and viability and also enable smart community. So essentially the idea is that if we can make the system as cheap and also as convenient as you actually owning a personal car, so a lot of people can actually use it. So that's a kind of a vision. But the question is, how do we actually go from our vision here to there? Right? So this is where we're actually looking at some of the research problems. So one of the kind of basic research problem we're looking at what are the demand for such a service, and we actually use the demand to understand the efficiency issue. So essentially understand, is such a thing doable? How many shared AV we actually need, for example? And also we had to look at the economic issue, how much is the cost, etc., and the business model. Now, obviously, then there's a lot of system design issues. How do you actually deploy such a service to make it as cheap as possible, as convenient as possible? And then also we're looking at what it impact on how we actually open to redesign the city, the street, etc. So for this, we actually want to work with the community at the different levels and looking at the societal problems. So we actually also kind of envisage a few kind of pilot projects that's going on in the Twin City and the Minnesota area. So I just kind of briefly talk about each of the research problems. So we list the basic kind of problem we actually look at. So we're going to actually provide you some highlights how we actually address some of the problems in the last 2 years. So in the thrust one, we basically want to look at the basic problem, even the traffic demand, the mobility demand at the, say, Twin City area. How many shared AV do we need if we have to serve the peak daily demand to meet the user quality of experience or service? Right? So you don't want to wait for too long if you want to call AV to go to work, etc. Right? And how would the AV actually impact the people's travel behavior? Would that, for example, increasing the travel demand or actually suppress it? So that's kind of one of the questions. So one of the things we want to actually kind of leverage is actually look at the Met Council travel behavior inventory survey and try to look at some kind of model issues. So this is more kind of on the technical side. This other technical problem, we want to look at how we actually design such a system. So this is going to be different than just designing your typical Uber type of service, which is a replacement basically for taxi service. So this is the problem we're looking at. How all the AVs, when you are not using it, you can have to place somewhere. So how do we actually design this so-called AV depots so that you can, when people call for this AV, you can actually serve the demand as fast as possible. So this is what we're actually looking at. For example, the traditional this ABC RAM in the downtown Minneapolis maybe actually service as centralized AV. People from the suburb with the AV, most of the AV can actually park there when there's no one actually request for service. And you could have a centralized, or you could have a much more distributed service. What is the different design trade-offs involved? So that's kind of one of the questions. And other questions, if we actually can forecast what the demand going to be, since AV is autonomous, it doesn't have to just sit, for example, in the APC RAM. Actually, you can anticipate people going to actually leave work now. You can actually go to certain places, like different office building, and line up at the street to wait for people and pick up so that people can actually get on AV quickly. Right? So also the issue of how do you design such a service? Most people live in the suburb, they come into the city, so you have kind of, should we actually do door-to-door service from the people home to the office, or we can actually go to, say, a drop-off location, for example, the ABC RAM, but within the downtown area, we're actually going to have a shuttle, automatic shuttle, pick people up and drop to different office location, etc. So that's a kind of different design service model that we are interested in looking at. So we want to kind of basically looking at a data-driven simulation-based framework to actually look at this design trade-off. We can't really build a real system, obviously. So we are looking at the data-driven simulation-based model. So the other issue we are looking at is essentially the economic viability business model. Right? So in particular, we want to looking at the efficiency versus equity trade-off. Right? So we don't want to design a system just to kind of minimize the cost. We also want to be able to serve diverse community. Just because of, for example, serve certain underserved community, maybe increase the cost, and we should not then decide not to serve this community. So this is kind of bigger picture issue we're actually interested in looking at. So what would be the service model? And should, for example, one is individual user actually own the AV, then having those AV as shared as a pool, called peer-to-peer model, versus, for example, you have Uber and Google type of services own the service and use it. So the question is, we believe actually managing the demand supply has become important. So whether should having this private entity compete, or we should have some form of public-private kind of partnership to design such a system. And what is the role of public transit in such a system? So these are a lot of kind of interesting questions, and we propose to look at, but I don't think we are able to actually solve most of the problem. The other things we actually, as I mentioned earlier, is the efficiency equity trade-off. So what kind of incentive we may actually provide to help address the equity issues, right? So this is where we believe, for example, local government and state level, the policy incentive become important to help design such a service. So I'm not going to go through the details. Other things, for example, the business can play an important role to provide, for example, subsidized services for employees and others to use such services. So the last thing kind of related to what I just talked about, we want to leverage the envisioned smart cloud computing service to tackle a lot of social challenging problems. For example, how to actually bridge the geographical or spatial disparity between where people actually live versus where jobs are located. So existing transportation system actually show that today we have a huge disparity. So this is a study actually done by a colleague, the co-PI Union Fan, who actually showed that this area for concentrated poverty where people live at one side, on the other side, for example, in the Southwest Metro, you have a lot of companies couldn't find enough workers. Right? So partially because of a lot of people in the lower income neighborhood, the current transit system doesn't really kind of provide convenient service to where the job is located. So the question, can we actually use shared AV to address such a problem? So other issues are looking at how AV is going to change the way we can actually design the street, the land reuse, and how we actually incrementally deploy such a service. So even if we have a future AV, we can imagine our community and neighborhood can be designed very differently. So a lot of parking lot can be actually being used for better space. A lot of parking meter on the street can be also be redesigned. So that's kind of the overview of some of the research problems. So all these things we actually want to do by engaging the community at the different levels. Right? So here we're just looking at some of the people who actually working with, both as the policy decision makers and also infrastructure facility provider and the service providers, and then also the user community and the destinations, for example, various businesses. We're talking to all these people to help us understand and the perception of AV and what they imagine AV can actually help address a variety of societal issues. So in particular, we are leveraging some existing ongoing and future kind of project has already planned by, for example, MinDOT, et cetera, looking at working with those organizations to think about the role of AV in this project. So in the proposal, we actually envision a kind of 5 pilot project, which I'm not going to talk about. What we're going to do in the remaining time, I can actually transition to Yanhua. We're going to give you some kind of idea of what we have done. And in particular, the first thrust 1 or 2, we're going to actually spend a little more time to talk about, which Professor Yanhua Li of WPI are going to talk about. I'm going to take over just briefly, talk about some of the other research activity, looking at the economics and operation of AV, some of the social challenging and the community engagement project. So Yanhua, I think is so sorry. I have problem moving this move forward. So let me just stop the one. Yeah, are you there?
Yes, yes.
Yes, okay. So
yeah. Okay, great. So thanks, Professor Zhi Zhang, for the overview of the project. And now it's my turn. I'm going to zoom in to the individual research thread and to introduce our preliminary results on each thread. So the first one I'm going to talk about is the feasibility study of our proposed smart and smart cloud commuting system to study, okay, using this smart cloud commuting system, how many self-driving cars we need. Okay, so yeah, this slide shows the brief overview of what we are envisioning for having this smart and commuting system. This is a concept we borrowed and kind of extended from the so-called cloud computing system. See, cloud computing system we have now is like we don't need to have our computers. We could borrow, or lend some computing resources from Amazon, for example, to compute and things for us. All right, we can just rent some resources from Amazon. But for the smart cloud commuting system, we are envisioning that in the future, when we have the self-driving cars, all right, we can have a cloud of self-driving cars over there and serving for passengers whenever they need the trip. Okay, so in this case, we look at this picture. It's like, when there is a passenger who want to travel from one place to another, you just send a request to the smart cloud commuting system. The SCCS system gonna assign a self-driving car to take the passenger from the source to its destination. Okay, and so in this case, we want to study, say, given this idea, all right, how many self-driving cars we need and how to deploy them into the urban system to serve those passengers. Okay, so next slide. So to deploy and design such a smart cloud commuting system, we need to answer 3 key questions, all right, in this system. First of all, how many self-driving cars we need, okay, in the system to serve the passengers? And secondly, where to deploy those vehicles? Okay, we have a larger city and the trip demands emerge everywhere over time. Okay, where to deploy those vehicles? And lastly, how to dispatch and route self-driving cars to serve the passengers. So in this work, so I'm going to first talk about our preliminary results for the first question. Okay, so say how many self-driving cars we need. And to do that, we model this smart cloud commuting system using as a queuing system. As shown in this picture, we viewed an entire self-driving car system as the middle, as the box in the middle. All right, we have a pool of self-driving cars deployed in this urban area, and we view all the passengers, okay, coming into the system as a queue. They're coming into the system one by one with their request to travel to their desired destination. All right, so the passengers coming into the queue and being served in the queue. First come, first serve. And each request may have a different requirement, basically in terms of where they want to go, how long this trip will be. So the serving time for each passenger may be different. Someone we may need to travel longer time than other passengers. All right. So with this queuing system, we have some kind of a little bit of math to characterize this queuing system. So next. So we have the passengers coming into the system. We characterize their arrival rate in terms of number of passengers arriving into the system per unit time, for example, per hour. And for the service time, once a passenger coming into the system, it may be served with different amount of time. We have the service rate characterizing the number of passengers being served in a unit of time, for example, 1 hour. And also with the arrival rate and the service rate in this queuing system, we can characterize the utilization of these servers, these cars, as a ratio between the arrival rate and the service rate. So this tells us basically how much a vehicle is utilized over time. We want the cars, the service being utilized as much as possible. We don't want to waste the resources. We want to have the right amount of resources, the vehicles in the system. Okay, so with this queuing system, we actually use real-world data using large-scale taxi data from Shenzhen, China, with 595,000 daily trip demands. And using this data, like the picture on the left, it shows the clear diurnal pattern of the trip demands. Okay, every day they have similar pattern. And so with this data, we can quantify the arrival rate of the passengers. So like on the shown in the right-hand picture, it shows the arrival rate follows a Poisson distribution with the parameter, the arrival rate as lambda as 8.442. Okay, so with this travel demand information from real data, we'll further analyze, basically using our idea of self-driving car system, smart cloud commuting system, how many self-driving cars we need to replace all the taxi drivers, whether we're gonna get a less number of self-driving car needed or more. Okay, so the next slide will be our results. Okay, so this picture shows our preliminary results, interesting result. It shows that, so the x-axis is the number of depots we're gonna deploy in the urban area. We can see, all right, when we deploy only 4 depots, okay, in the urban area, each depot have certain number of self-driving cars. Okay, we only need like 9,500 self-driving cars to serve all the passengers, okay, with the similar service time around 40 minutes for each passenger. All right. Remember, in the data set we have, okay, the taxi drivers, the taxis in the system, okay, from the data, there were 9,600 taxis. All right. Using our idea of the self-driving car system, by deploying 4 depots to host those self-driving cars, we only need 9,500. It's less than the taxis we have in the system. All right. The x-axis is basically once we increase the number of depots. Say we have more depots deployed across the city to have the self-driving cars getting closer to the passengers. Okay, once we have more depots, we have vehicles closer to the passengers. Say once we have more depots, we can only need smaller number of self-driving cars to serve the same amount of trip request. All right. For example, when we have 8 depots, 16 depots, 32 depots, we only need 7,500 and so on and so forth. I mean, there's a smaller number of self-driving cars we need. It's significantly smaller than the number of taxis in the system. Okay, so we can reduce the vehicles needed. And moreover, when we compare the utilization with the current taxi system, so the current taxi system only have 42% of utilization rate for the taxis. That means 42% of the time the taxis are busy, and 58% of the time they are idle. But using our idea, when we have 32 depots, the utilization of the self-driving cars is 90%. Is high. Okay, so this is the first work we have done for basically studying the feasibility of this smart cloud commuting system. All right, so the next part, I'm gonna look into the thread 2, our preliminary results, by looking at how we're gonna design the transportation mode to better serve the passengers. Okay, next slide. So to do this, okay, let's first have a quick view of today's transportation system. Okay, if we look at today's transportation system, we primarily have 2 transportation modes. One is point-to-point modes. You can think of those like Uber drivers and Zip cars. You can rent a car from Zip car, and also taxis. So those are point-to-point mode where the vehicle gonna take the passenger in basically in the trip from the source directly to the destination. And in this point-to-point mode, it has some pros and cons as well. So first of all, its advantage is that the travel time is short because the vehicle can only serve for this passenger, not taking other passengers. And the problem is usually the Uber and the taxi with a higher cost, okay, compared to other transportation mode. And the other transportation mode is we would call it a fixed route mode, including the bus route and the subway trains. So the advantage of this transport mode is that it provides affordable service. Okay, by sharing the service, the cost is low. But the problem is this type of service, passengers need to follow the fixed routes and fixed timetable. Okay, so the travel time could be long because along the trip from source to destination, the bus may stop, a couple of other stops to take other passengers. So both of these transport mode have pros and cons. And what we are envisioning is that we want to have a hybrid transport mode that can still keep the advantages of these 2 modes and without those problems. All right, so the goal is on the right-hand side is we want the system to serve the dynamic needs, okay, dynamic trip demands from the passengers. And we wanted the travel time when serving the passenger to be as short as the point-to-point mode. And the cost of the service will be as low as the fixed route mode. So we actually borrowed the idea, so-called hub and spoke, already being deployed in some system today, like in the airline system. When we take the airline from source to destination cities, we may need to go through a hub city, okay, to reduce the operation cost. And also this hub and spoke system, say with a huge hub locations to better serve the passengers. This also being deployed in the packet delivery system. All right. So the challenge of our problem is how we can basically deploy this hub and spoke mode system into the smart and a smart cloud commuting system with self-driving cars. Okay. So next slide, I want to show you our idea of the system, basically by comparing, in a toy example, by comparing this hub and spoke service with the existing point-to-point and fixed route service. So in this case, let's look at one simple scenario. Say we have a whole bunch of passengers who want to travel from their source location to their destination location. All right. So we're looking at the same scenario. We have 3 source locations, S1, S2, S3, and 4 destination locations, D1, D2, D3, and D4. See, in this case, let's move on to next. So we're gonna have animation showing the request. Okay, moving on, keep on going. And we wanna show the direct trip from the sources to the destinations. Okay, so basically the trips are from, including passengers from S1 to D1. There are group of passengers who wanna travel from S1 to D1. And also group of passengers want to travel from S2, the same source, to D2, D3, D4, the 3 destinations. And from S3, if we click more, we're going to see, okay, from S3, we have passengers from S3 who wanted to travel to D2, D3, D4. So in this case, we have a group of passengers with their trip demands, okay? If we use the point-to-point model, that means basically each source destination pair, we need a dedicated, basically a vehicle or shuttle to take all the passengers from source to destination. So we look at the picture on the left, we need in total 7 autonomous vehicle self-driving shuttle to take the passengers from their source to their destinations, 7 AVs, okay? But using our idea of the hub and spoke system on the right-hand side, we're gonna basically, for the source S1 to destination D1, this trip, there are more passengers. We still just use one dedicated AV to serve those passengers. But for those source S2, S3 to destination D2, D3, D4, we use shared vehicles and with 2 hub locations, H1 and H2. In this case, the passengers from S2, no matter where their destination is, they take the same shuttle from S2. And when they reach the hub H2, they're gonna take another shuttle to reach their destination, D2, D3, and D4. The same thing for the S3. In this case, we count the number of vehicles, self-driving shuttles we need in hub and spoke. In this case, we only need 4 self-driving shuttles. We reduced, in this simple example, reduced the total number of shuttles we need from 7 to 4, okay, comparing to this point-to-point service. And so this slide, we're gonna show comparing our hub and spoke service with the fixed route service. For example, bus routes, okay? On the left-hand side, we show the example of a bus route. Say the passengers can take buses with multiple stops. In this example, we showcase, for example, in this case, we have 27 stops that these passengers need to basically stop at, before reaching the destination. And using our hub and spoke idea in the urban area, okay, we only need 2 hub locations, significantly reduce the number of stops the passenger needed to wait, okay? So it reduced the number of stops from 27 to 2. So in these 2 examples, we actually, compared to the point-to-point service, we reduced the operation cost. So the costs are going to be lower than point-to-point. And comparing to this fixed routes, we reduced the number of stops. That means we provide better service, shorter travel time. So this is the example we want to show to showcase the idea of the hub and spoke. So next slide. So for this one, we move further. Say we have the idea of hub and spoke in the city, But we don't want to say replace the fixed routes and point to point in one shot. Okay, we don't want to shut down the transportation and in one day we replace everything to the hub and spoke. We want to have our system to be integrated to the current transportation system, say compatible with those existing transportation systems. So this part is done by Alireza in civil engineering department. Is part of a project. So Alireza has done some interesting work, for example, by integrating this system, this self-driving car with the current transportation system. For example, in this case, Alireza developed this mobility on demand system. Say they have a MOD, mobility on demand system, to estimate the future demands, get a good estimate, and using this estimated demands to basically do driver payoff and driver participation to only basically have the right amount, the right number of drivers to serve the predicted future demands. So this is the integrated system, developed by Alireza. All right. So so this is more detailed work with visualization and data in Minneapolis area, and so this basically shows showcase with the mobility on demand system to predict the future demands plus the transit system, how this is going to work, using an example to the MSP, the Minneapolis airport. Okay, let's move on.
So I'm going to take over. I think we have about just 10 minutes or so time. So let me just quickly kind of talk about some other research activity has done by our colleagues and give you a kind of flavor of the different type of problems. So I'm going to pretty much just flash through the slides since we don't really have time, and we're going to share the slides with you anyway, so you can actually take a look at the details. So one kind of major research for us we are looking at is looking at the economics and operation of autonomic system, right? In particular, looking at the ownership scenarios, for example, different type of peer-to-peer versus business to consumer, customer. Right? So what is the kind of different kind of modes when they're dominant? Right? So and how they actually can possibly affect the pricing, the differentiated services, etc. Right? So those are kind of problem led by Professor Saif and Benjafar and his research group. So I'm not going to go through the details actually. So let me just quickly flash through some of the problem he has studied. So one is to try to look at the equilibrium model and looking at the, suppose you have a peer-to-peer system where basically the AV are owned by individual users, you put in a pool to actually design the system we talked about. Another is having service provider like Uber, Google, maybe a transit provider own the car and have the customer use that. So basically what is the mode going to be dominant? This a lot had to do with for example, the cost of ownership, etc. So I'm not going to go through the detail of what the study. So this study also show actually the role of government that can potentially pursue incentive and other regulation or policy can induce certain desired outcome. Right? So for example, if you want to break certain monopoly, we can actually provide certain policy issue. So the other problem Saif and his group have looked at is looking at this hybrid on-demand model, especially with thinking about incremental deployment. We're going to have a conventional cars versus AVs coexist. Right? So how would, if you have a service platform that's going to use both type of cars, what would be the impact on the overall cost, etc. So this is the one study that they have done. Again, it can depend on a lot of on the cost supply model. For example, in the conventional kind of Uber type of service, the driver, the availability of driver, and also the cost of driver going to play an important role. So that's the other set of study that Saifa had done. So, oops, sorry, I have some problem with my my mouse. It's not working properly. So other part we actually look at is essentially look at analytics, economic modeling in the overall design planning operation. So you already heard about some of the architecture design, for example, hub and spoke model, research. So the question is, what is the different kind of cost, right? So how many vertical we actually need. So this is actually all depends on going to impact the cost and the pricing for the consumer, and also how we actually place the AV depot is going to impact the quality of service user can expect it. So this is the set of problems we have been looking at. So for example, what is the optimal fleet sizing? Again, based on certain theoretical assumptions, simplified assumption, we can actually model the system to getting some insight into the problem. So the other part is also this optimal depot location. Right? So where do you actually? So there's a different way we can think about AV going to go back to depot and become idle and park on the street. And what is the cost of capital cost of designing the depot? So if you have more depots deployed distributed, you're going to help to reduce possibly reduce the QE, the cost, the user QE, but you can increase the cost. Right? You have more location. You also have to kind of essentially balance the load. So this is a different kind of trade-off we have to look at. Again, we are looking at some of the queuing type of model and through also simulations, study this type of system. Again, this is kind of application of the Twin City area network. So this is a result, this is research done, led by Alireza. So I'm not going to go through the detail. So I'm going to just spend the next few minutes to quickly talk about some of the community impact. Actually, it's not something happened with my mouse not moving. Right. So we're looking at some of the social challenges and the community engagement activity. So one of the problem we're looking at anticipate what the possible problem for the future AV on the physical infrastructure and how we can tackle the social challenges. So this is the work mostly led by Professor Tom Fisher and also Ying Fan and Frank Luma. So again, this what's happening. So this part, we just kind of show you some pictures of looking at what we envision would be the future, how we're going to actually design street differently. So once you have AV, and you probably can eliminate a lot of parking street, but on the other hand, you may actually design street to actually make it easy to actually do curbside picking up passengers, etc. So this is some of the picture that drawn by study done by Tom Fisher with the visualization of what's actually happening. I'm just going to flash through some of the slides in the interest of time. So the other thing we have done, so this is a project led by Professor Ying Fan and Frank Luma, is looking at the community survey, try to access the potential for AV, right, to understand how the community actually perceive AVs and how AV can, for example, address the spatial mismatch. So the idea is to actually conduct survey using kind of select representative sample. Here we actually design fair surface survey based on the kind of tablet people can look at interactive survey, collecting a bunch of questions I'm not going to actually talk about. And in this survey, we actually recruited people. So this slides picture here show where the responder actually coming from the Twin City area. So we use, for example, a variety of ways to actually recruit the responder using social media, for example, getting people to respond to the survey. So there's also a next set of kind of other community engagement I'm not going to talk about. One particular one, the interesting one is actually work with Hitch Health, which is actually currently using Uber to help actually getting people living in a low-income community to go to hospital, make their appointment. So essentially automatically pick people up based on the appointment they have with their health. So we're also looking at how future AV can even further improve that services. Right. So anyway, so that's kind of give you kind of flavor of what we have done. So one of the kind of challenge, obviously, many of you probably have similar questions. So how do we actually evaluate the success, right? So impact. So I mean, if you look at the study we have talked about, we're basically using two set of metrics. One is looking at quality of the service, the wait time, trip time, what is the user experience. Another is looking at cost and also accuracy issues. So, so the one thing we have been struggling is that, okay, at the end of project, what should we consider the project success? So what type of outcome we should look at? So is that in the term of some kind of simulation model, tool, platform we actually build, help people build, or is more kind of about policy recommendation, guidelines, etc. So those are kind of challenges we're actually facing. The other problem we're kind of challenging we're looking at is basically data, right? So how we're actually getting a lot of data to validate study. So this is also we're likely getting help from you also. Right? So we want to have transportation demand data, travel behavior. For example, some of you can help us collect data or participate in some of the surveys. Right? So there's also a lot of different type of data source out there. So how can we actually integrate those sources together for this particular study? So this is just a list of different type of data we're actually interested in looking at. Some we can actually get in from the open source, but a lot of are not available. So so that's why we also engage some of the kind of survey and etc. So this is the kind of challenge we're facing. So in the kind of maybe do we still have 5 minutes, so we can do quickly?
It's 12:29. Probably have
Right.
1
Right. So I know the scheduled time is 11:30. Maybe we can just within 5 minutes to kind of talk about some of the project we're looking at is given that there's a diverse different type of data, how we can actually employ, for example, machine learning AI to help us to design future transportation system, but also potentially also address some of the issue with the data, shortage of data. So I'm going to just switch to Yanhua again. You can quickly maybe talk about the how you actually the work you're looking at the learning human decision strategy. Maybe
Yes,
just quickly talk in 3 minutes.
So yeah, as Professor Zhang mentioned, so using AI, we are trying to better utilize the data, because to designing this self-driving car system, smart cloud commuting system, is a complex system to serve so many passengers in a large scale of the city. So we are thinking of, okay, now in today's urban system, we already have many experts like the taxi drivers. They are expert of finding passengers, serving passengers. Why not we learn from them and borrow from them before applying and designing our self-driving car system? So our idea is by collecting those data from the human decision makers, like taxi drivers, food delivery workers, we have a giant amount of data. We call it the human generated spatial temporal data. And we're going to use AI to design the so-called spatial temporal imitation learning, basically imitating and learning from the human decision makers in the urban area to learn their strategy and plug in and integrate their strategy, their expert strategy into the self-driving car management system. All right, so next slide. So the idea is we using the spatial temporal imitation learning framework to learn the experts' decision-making strategy that can be applied to solve many real-world problems, including how to design the self-driving car system, and also how to train the taxi drivers, how to design the transit system, etc. Okay, so next slide. And so this is just a quick example of showing you how to model the decision-making process of a human agent. Like this taxi driver, we can view as if this taxi driver is transitioning from a sequence of locations, okay, in each red box. And at each red box, when the taxi is idle, the taxi driver, if it's a smart taxi driver, he knows where to go next, which direction to go next to more likely find the passenger. So we're gonna model the decision-making like this trajectory of transitioning across different locations and use artificial intelligence, use deep neural network as a function to learn their smart strategy. And so our plan, yeah, next slide. Our plan is by using this strategy to work on, first of all, the travel behavior inventory data collected in 2019 from Met Council with 351,000 trips from 16,000 people. And we're gonna try to use the imitation learning technique to learn from this data from, for their strategy, and basically have a way to generate like real TBI data to facilitate our system planning. Okay, yeah, that's our idea.
Right. So basically the idea here is that there's a lot of diverse data already out there. Right? So the question, can we actually integrate such data and also use data actually building what we call the using genetic deep learning model actually kind of augment the traditional modeling. For example, one traditional modeling approach is the activity-based modeling for forecasting. Met Council has used that to actually forecast the demand in the future, but also can be used, for example, make decisions on a daily system. So we actually know that the genetic deep learning can actually take in some data, actually then generate synthetic data. For example, some of you probably have heard about, you can use the images, then generate new images that is actually not real. Right? So the question, can we actually do similar thing and generate this demand, and we can use that to help us to study the future AV. So that's the kind of the this project we're actually interested in looking at. So anyway, so that's basically conclude what we actually what do we actually want to say. So the, kind of in the end, we basically actually need your advice, comments, right? So your ideas to help us actually improve the project. Right? So here's a set of kind of questions we're actually interested in find the kind of comments and suggestions, etc. So that's what we actually want for you guys. So anyway, thank you. So I think it's time for Q&A.
Yep, thank you all.
Thank you, Professor Shang and Professor Lee. It's clearly a lot going on, complicated topic, and we're lucky to have about 20 minutes to try and get at some questions here. So please feel free to type your questions into the chat. If you've got a longer, messier question, you might want to just type in a question mark and we'll unmute you and ask you to state that out loud. As a moderator, I'm going to take advantage of that spot and ask the first question. And given it's such a complicated issue, there's so many moving parts. It's a great time to be a researcher, but I think it's equally a difficult time to be a practitioner. And I'm just wondering if you could talk a little bit about what do we know at this state? Do we know that unregulated, everybody owning their own automated vehicle is kind of a disaster in terms of congestion and climate change and parking and, just clogging up, drop-off locations, and that, we need this shared model and it can dramatically reduce costs and it can dramatically reduce impacts on the system and environment and provide reasonable delays. Do we know anything about infrastructure impacts, where drop-offs might need to be located, some sense of scale of these drop-off pickup locations? Do we know anything about capacity on the system? Because I know we talk a lot about how reduced headways with AVs can really increase the capacity of the system, but a lower cost opportunity to travel could dramatically increase the demand for travel. What do we know for MnDOT, for cities, counties, the Met Council that is making decisions on a daily basis? What do we know at this point?
So I'm going to take a stab now try to answer your question. I think this is all great question. I mean, the simple answer is that no, we don't know. At least I don't know the answer to a lot of questions you posed about. But nonetheless, I mean, this is exactly what we actually want to do this study. Right. So, for example, you mentioned about the impact on infrastructure. This is what Tom Fisher has been exploring, working with on the local government, try to understand how the future streets should be designed. But I mean, basically, I personally believe, if we don't try to think ahead, right, so just let people to buy their own AVs. We already had some horror story. Right? So Tesla, for example, a car you could have some self-driving ability. We already see some videos on the internet. People have AV, they are sleeping or drinking and eating in the car, right? While you also have a lot of different conventional AV going around. So the question, for example, if you have enough people going to have AV, should we actually have certain dedicated lanes, or should these people, because they can afford AV, then you have dedicated lane, right? So this is a lot of questions we don't even know. So I mean, that's why we firmly believe on that that having a shared AV system, especially in the, I believe, for example, in the downtown and where places where you're more likely to have congestion, it can make a lot more sense. And I can imagine, for example, and this is already true. For example, my younger colleagues who get recruited in the university, many of them actually don't have own a car, right? So they live in the city, they just go to call Uber or Lyft for if they want to go anywhere. Obviously, the COVID-19 going to change things somewhat differently. Right? So, so kind of borrowing from the future pandemic and other things that happen, I think this sharing AV has been a trend until the COVID-19 happened. And personally, even myself, right? So when I going to travel, before actually for certain places, especially in the suburb or conference, I would rent a car. Nowadays, I actually don't rent a car anymore. I just go there and then call AV. I mean, based on not call AV, I call Uber and Lyft for the service, right? So I think as long as it's convenient enough or cheap enough, a lot of people are going to use it. So that's for me, it's the challenging of I think the goal we try to accomplish. But that doesn't mean that the individual people are not going to buy their own AVs. I think that's actually fine. But if the majority enough of people, especially for commute, they're going to use AV. So I can imagine even for highway commute, maybe you have more this hub and the hub and the spoke model, right? People may actually go to either driving your conventional car, and then maybe the highway, instead of having, we have a kind of AV shuttle going, people going to downtown, etc. So anyway, so I don't think, I haven't seen anyone who provide a clear answer to all the questions you posed. I mean, this might take, while you may have additional comments.
Yeah, well, this is a great question. I mean, having the self-driving vehicles would definitely have significant impact to the urban infrastructure, so on and so forth we have now. And a part of our team in this NSF project, I think we also studied the land use, okay? The impact of land use. So for example, the parking space, once we have self-driving car, the car after sending the passenger to the destination does not need to park next to the passenger. It can go back or go to serve other people. So the land use could be significantly impacted. And I think, in our team, we didn't present today, but that's something that we are looking at.
Thank you both. Professor Lee, if I could ask you a question about some of the modeling you did and how you considered the transition between one trip to another. I know, say in a transit system that exists today, that's a large cost to the user in terms of scheduling and waiting time and things like that, and just how you considered that.
Yeah, well, that's a good question. So especially in the urban area, the trips are basically, demands are changing dynamically. So in the morning rush hour versus noontime versus the afternoon rush hour, the trips are dynamically changing. It's hard to plan ahead of time. It's hard to use a planned routes and timetable to serve the dynamics. So what we are going to do is we're gonna basically, similar to the mobility on demand, we're gonna have a system to predict, using big data to predict how many trip demands there will be in the next 1 hour or two. Okay, once we have an accurate prediction, we know in the next 1 hour how many trip demands there will be. We're gonna dynamically design the basically the shuttles, okay, to serve the passengers. For example, we're gonna have the shuttle to serve the passengers basically from the source to some hub station, and the passenger is going to get off in the hub station and take, like board on other shuttles to reach their destination. We're going to have basically the demand prediction system to predict the future demand and use the dynamic basically algorithm to dynamic plan for the autonomous shuttles. Yeah.
Right. So I think, Tony, your question is the operational side, how you actually design this transition. Right? So the other things we believe so that, for example, a lot of kind of, based on my understanding, my impression, a lot of people, for example, may not take, for example, public transit. Partially, when you do transfer, it's actually complicated. Right? You say where going to the next one, etc. So this is where I believe the future mobile technology can help. So we can design the system in such a way that make the transition from one shuttle to another much easier, simpler system. Right? So once that with people have a mobile phone, you can actually know where exactly the next place you can pick up, where you're going to go to the other shuttle, next shuttle you're going to be, how long you're going to wait, etc., where you have to wait for it. Right? So the other things could be also, this is something might be interesting, even that we have this possibility of Easter shuttle for this Apple, the White Bear makes, right? So the design, for example, shuttle itself may have a kind of a lot of information to say, hey, where you should go for the next one for people who don't own a smartphone, for example. Right? So the question, we can possibly also make the physical infrastructure smarter to let people know, hey, where you should actually pick up your next transit, etc.
Yeah, a simple idea is basically we can borrow the idea from the airport management. The passenger just get multiple boarding passes, okay, before starting their trip. Okay, the first shuttle use the first boarding pass to find the red gate to board, and in the transit, in the hub city, in the hub location, use the next boarding pass to find the gate to board. Something like that.
Thank you both. Yeah, I think that's going to be pretty important to a hub and spoke design, just because that transition could be very costly from the user perspective. Professor Zhang, Gina asked a question that you started to get at when you mentioned COVID, and if you could expand a little bit on, let's see, do you have plans to update your models? When do you think you'll have enough data to update models to reflect the COVID changes in travel patterns?
Right. So this is study on the Ying and her team actually looking at some of the survey. I think we designed the survey actually before the COVID-19. So we're thinking about maybe also design a new set of survey to look at people's perception of AV, or in general, just a share, right? So whether you're winning healthy to, I mean, you think it's safe to take say shared Uber type of services, right? So it's definitely going to have a positive impact on that. I mean, in a completely kind of separate project, I've been talking to my colleague Nikos and other, looking at you can potentially also design robotic system. So you may have ultraviolet blue lights to actually automatically actually kind of what the right word, and try to essentially clean the car, whatever. So maybe help. It's mostly perception of possible safety, health risk. So I don't really know how that's going to affect people's perception. But on the other hand, AV also going to have other uses. So for example, for food and other delivery, that might become useful also, and for health also.
Great. And Steve Misgan is asking the always obligatory question when we talk about AVs, and it's an unfair question, but it's a very interesting one, is when do you think we'll start to see AVs appearing? What does that transition look like? I think some people talk about freight showing up first, or maybe small scale delivery in urban areas. When can I use my phone to call up an AV is probably what he's getting
right.
at.
I mean, so this is a great question, right? So I think I mean, whether we talk about US or other places, so this can be also quite different. Right? So we know that there's already trial going on in Arizona, Tempe, and Pittsburgh, and so you already have some AV, right? So we also have Tesla is almost, I mean, it really depends on what is the level and how people actually feel safe with some of this technology. And so with the fleet, like a truck going on, so it's again depends on, I think there are a lot of policy issues. As I know, I read some article just a couple of years ago, maybe even just a year ago, talking about Georgia, their equivalent of MnDOT was looking at design, spending like $1 billion to design highway just for the fleet trucks for delivery. So that might be something happen, right? Again, it's the infrastructure cost. So I don't really want a prediction, but on the other hand, I can see some other places like China, I know, which is not as regulated. They may have stuff going on because it's a lot of things happen bottom up. Some company just decided to deploy things, and people not consider all this safety and other considerations. So I think this is the strength of US. We want to anticipate what are the different trade-offs to study, help guide the policymakers. But on the other hand, it's also the business like Google, Uber, they have been essentially taking the traditional computer science approach. We develop a system, let it use, right? So then become dominant. Then the regulator oftentimes fall behind. So that could create a disaster. So that could be potentially have a very negative impact on AV. People may have a negative perception, which could potentially push deployment AV or better AV service back a few years. So this is where I think the research community and the policymaker community and the general community need to work together to understand how AV can help, but also what a potential negative impact it may have on the society. We're trying to mitigate this impact.
Yeah,
so I think a probably smaller scale deployment will be useful. Right? So that's what I hope the Whiteback Lake, the pilot project with AV, and people can say, hey, this is actually can be useful. Maybe I can push the deployment more.
Yeah, from smaller scale to larger scale. Yeah, so as Professor Zhang mentioned, so in this project, we're gonna have 2 autonomous shuttles, right? Probably being launched and used early next year or sometime. That's gonna be the starting point probably for University of Minnesota area to have this, on service.
Yeah, that's
right. So that I think there's some of the perception. So this is also we want to try to push the AV shuttle type of service. A lot of people think about AV, they're thinking about just a passenger car and Tesla type of stuff. Right? So, so that's not what necessarily AV is about.
Well, thank you both. Great presentations. We learned a lot, and appreciate the chance to ask some questions. This is also part of our regular meeting of the Safety and Traffic Flow Council, and with that, we have some time to share what attendees are working on. And it looks like Katie has entered a few questions that can prime the pump. And so everybody's welcome to enter into the chat, or if you want to just mention in the chat that you'd like a chance to speak, we can unmute you. See what, so the questions Katie entered are, what current transportation safety and traffic flow issues are you and your organization facing? Do you have any organizational information or event updates to share? And what ideas do you have for potential future safety and traffic flow council meeting topics or speakers?
Tony, this is Gina, and I can maybe kick things off with an update from CTS that hopefully folks are aware of, but I thought I'd just give a little bit more information. This summer, we were successful in securing some funding to purchase or enter into some leasing agreements for connected and automated vehicles that can be used for research here at the university. So we'll be taking, or we're deciding this week on the vendor that's going to provide a highway speed type vehicle to the university. And if the contracting process goes well, we expect to have that vehicle available for research starting at the end of January. And then we're also entering into a partnership agreement with another project to have access to a transit type shuttle that can be used. Right now, we're thinking that for some of the research that could be used for engagement and public acceptance type research and work. And then finally, we're just finishing up a strategic research plan for the university around connected and automated vehicles. And I expect that we will share this at some point, you know, with this council, because I think that there will be a lot of interest in that. But the hope is to kind of establish those areas of research where we think the university can make a real contribution. And apropos of today, one of those is in cold weather operations of automated vehicles. So I'm certainly glad that we're all sitting hopefully warm and comfy and safe while the snow gets started here. And I'm going to go back on mute because the garbage truck is outside. So.
Thanks, Gina. And I know we invited MnDOT's CAVX office to share a little bit of update of what they're doing, but the scheduling didn't work out. But you know, they've got a group of committed staff there that's always thinking about policy, always looking into learning about these issues, and we'll look forward to them joining us at a future meeting, I hope. At the Met Council, you know, I don't know that we're doing a whole lot. We're definitely trying to keep up with what's going on, with what the U's up to, and you know, learn and think about what is ready for prime time. But I don't think we're there quite yet in terms of making policy and investing dollars. But I don't know if there are any other agencies that want to speak up a little bit about what they're up to, or any ideas for the Safety and Traffic Flow Council in the future. We can give it that awkward minute because I know it takes time to type too. I guess I want to. I don't see anything coming in yet. You want to close it out, Steve?
Sure. Again, thanks, professors, for presenting very interesting topic. And I look forward to seeing a conclusion of your research. Again, a reminder to everybody for the CTS Research Conference. Registration ends on Friday. There's a web link earlier in the presentation. If not, just go to the CTS website. It's the #1 thing on there, just hit the link. And then also there's another council meeting next Tuesday, I believe. We mentioned it early. I don't have a list of it here, but it's on the website as well. Please take advantage of these seminars. It's a great way for the U of M researchers to get their information out to us practitioners. So Gina, do you have any last words or?
I don't, just thanks to everybody for participating today.
So we'll have a good day. Enjoy the snow.
Thank you.
Thanks, bye.
Bye-bye.
Thank you all.